Morning, everyone. So over the last 2 days, we've been looking at voltaic cells. Essentially, it's setting up a spontaneous chemical reaction. We're going to do half on one side, half on the other side. That way we can force the electrons to flow in one direction and actually taper off the electrical energy. I'm going to give you a quick practice question here, see how we do is sort of matching terms on a table. We'll go from there. So just for warm up here. I'm going to give you an electrochemical cell. Electrochemical cells or voltaic cells here will standard have two beakers, have two sides of the container. On the one side, I'm going to put in platinum electrode, a carbon electrode. What's nice about these two here is these two are known to be inert electrodes. Inert meaning they are unreactive. So when you're making that list of chemicals to look for on the table, you don't need to worry about looking for platinum or carbon. I'm going to give you for this time, let's say we have a solution of 1 molar KMnO4, potassium permanganate. We'll see more of this in today's lesson as well. On the other side here, let's make it, we'll set up a contraption where we can actually bubble in a gas. Let's put in H2Se as a gas. I still need to hook up wiring for my electrons to potentially flow through here. Depending on who oxidizes better or reduces better here, the electrons will always flow anode to cathode. And then we're going to have a salt bridge just to maintain some electrical neutrality. You'll notice all solutions are quoted at 1 molar for now because 1 molar is our standard conditions. Let's make this one here out of lithium nitrate, usually out of potassium nitrate, but lithium plus ions are also really unreactive, so it's a good choice for and salt bridge. Okay, so a couple questions I want to ask you here. I want you to determine the reaction and calculate the E cell. If this one here is all occurring inside a battery, you can pretend, like let's say it's a AA battery, as the chemicals react inside this battery, as the electrons are supposed to flow in one direction, what is the voltage that this gets at standard state? I want you to label the cell as best you can. So label and identify any observations at the electrodes. Does the mass increase? Does the mass decrease? Are bubbles forming? Is it acidic, basic? Those sort of observations. Okay, I'd encourage you to pause the video and try it out for yourself. Okay, assuming you've done that here, let's just take a look. The strategy for this type of cell, even later on we're going to switch over to a different type of cell. It's the same steps. It's just the chemicals that I play around with will be different. Your first step for all this is I want you to state exactly what you have. So for example, on the left side, I have platinum. Now I don't worry about that one. I have 1 molar. That actually tells you have water. I have KMnO4. I'm not going to find this as a compound, but KMnO4 is an alkali salt. That means I have K plus ions and I have permanganate ions. I do have lithium plus and NO3 minus. Those are going to counterbalance my charge for you, but usually the salt bridge, those ions, they are so weak at oxidizing and reducing, they usually don't interfere. How about on the right hand side here? I'm just bubbling in here H2Se, and I also have carbon. So I'm just making this list here. This is H2Se as a gas. I have carbon as a solid. Again, for the electrochemical cells, for voltaic cells, we definitely don't need to worry about platinum and carbon. Those are inert. And generally, we're going to find something has reacted before water does, but we can test it anyways. Those are the chemicals exactly I'm looking for. So if I have K+, I do not have K solid. If I have Li+, I do not have Li solid. Okay, so make sure you know exactly what you have. Now we're ready to look at our Electrochem table. We're going to start from the top left. The top left, they're all written as reductions. These are the strongest, although we have to call them oxidizing agents. These are the best at reducing. So it's actually ordered just like our acid-base table. Let's start from the top left and start going downwards. As I go downwards, I notice I don't need to look too far. I already found permanganate. Can I use this reaction? Well, permanganate needs to have acidic conditions for it to actually react. I wasn't actually told that it was actually acidic overall. So although I do have the permanganate, I have to skip this equation, keep going. Okay. I run into MnO2. Well, then that's not permanganate here. I do run into nitrate. Okay. But again, nitrate here also needs to be acidic, so that can't react here. Keep going, not the other acidic nitrate equation. Finally, we run into permanganate down here. Okay, so once you find your first match, this is the guy that does the reduction. Anyone else later on I'm going to run into things like water. I had lithium plus, I had K plus, right? Those ones there are so much worse than permanganate. That's why once you find your first match, there's your reduction. So let me just copy that equation out here. MnO4 minus in the presence of 2 waters. This is the non-acidic equation. Gains 3 electrons. On the table is written as equilibrium, but we've decided, no, this is reduction. So we're going to go one-way arrow. This ends up forming MnO2. I'm going to emphasize the state because that's going to help you with your observations later on. MnO2 solid and 4 OH minus. Let's state the standard reduction potential going left to right. The voltage is a positive 0.60. Okay. Remember, technically, if I just have one half cell, I shouldn't be able to get a full battery working here. But this one here is relative to the hydrogen cell. It's 0.60 volts better than H plus reducing. Okay. Once you find that half equation, then you get to switch over, go to the bottom right, and start going upwards. I told you before, well, we have lithium ions. We don't have lithium solid. Keep going. I don't have K. Keep going. Keep going, keep going, keep going, keep going, keep going. You don't need to go too far. We end up seeing the H2SC. So this one here, I'm going to sort of bubble in here as a gas, and then we're going to actually see what the reaction is going to be. Because the oxidation here has to be written right to left, I'm just going to rewrite it here. So starting with H2SE, it's going to end up forming selenium as a solid, and then forming here 2H plus and 2 electrons. Okay. The voltage here, this is the reduction potential. This is my partner selenium and coming forwards. They actually are 0.40 worse than hydrogen. I need to undo that going the other way. This gives you this half reaction is a positive 0.40 volts. Okay. The half equations on this chart are already balanced. All they ask you to do to find the whole equation for part A, let's do lowest common multiple. What did 2 and 3 both go into? Well, they both go into 6. Let's double the first equation and let's multiply by 3, the bottom equation there. So what is my overall equation? We have 2 permanganate. We have 2 times 2, so we have 4 waters. I'm not going to bother drawing the electrons because I had set up the lowest common multiple, so there's no free electrons in nature. H2SE, it needs to be multiplied here by 3. 3H2SE. We're going to produce then 2 parts MnO2, 8 hydroxides, 3 seleniums, and 6 H pluses. Okay, so you can just roughly check that the charges match on both sides. In that case, there should be balance. So we have a total charge here of -2. I would have 8 minus from the 8 hydroxides. With those 6 here, -2, -2, we're probably good. Okay, so the first question, that is the redox reaction. What is the total E cell? Well, the first part was 0.60 better than hydrogen. The other part here is 0.40 better than hydrogen. What's going to happen then is your total voltage is now going to be 1 volts. Okay. In fact, what you can do, you can actually, let's look back at our cell first. So let me just resketch it down here. So we had our platinum electrode here. On the one side, although earlier I had listed it as 1 molar KMnO4, we actually find the reaction is MnO4 minus, that's in solution, that's permanganate. It's a really deep purple, by the way. The permanganate actually reacts with water, sure, really plentiful in aqueous solution. It ends up gaining electrons that arrive here, and what end up happening? They end up swimming up close to the platinum, they get reduced, they gain those electrons, they end up producing MnO2 as a solid. Well, a solid is going to start plating out and chunking out in solution here. Those little pieces are going to be MnO2 solid, and it's also in the process going to release off hydroxide. So in the process, we end up creating OH minus. So this is where reduction occurs, right? Reduction is when electrons are on the left-hand side. The MnO4 minus has been reduced. The site of reduction is the cathode, right? Even though the platinum isn't doing anything. It's just a temporary holding place for the electron so the permanganate and water can come in close enough and gain those electrons. Where did these electrons come from? The electrons had to have come from the other side of the table. Again, the plate we used was carbon, right? It's inert. We had bubbled in H2SE, right? That one there is a gas. So H2SE, right? I bubble it in. H2SE ends up dropping off selenium deposits, so it's going to still play it out as Se. So we're going to get chunks of Se solid coming out, and we're actually going to get H pluses off of this as well. Okay. Even though the overall equation, well, this is silly. Why am I putting like hydroxide and 6H plus? Usually if I were balancing, yeah, I'd make maybe 6 hydroxide, 6H plus make 6 waters in the net of hydroxide. But you actually see better in this equation. In fact, the hydroxide is generated on one side and the H plus is actually generated on the other side here. So if I were making some observations here, the cathode, we said we played out MnO2. We can say on this side, the mass increases for the cathode. We are actually gaining little deposits of MnO2. It's also generating hydroxide. This time it doesn't have that 10 to the negative 7 as you saw yesterday. This one here is actually producing hydroxide. This side here is actually getting more basic. So how you can frame that here is you can say the pH increases. Sometimes in questions they'll even throw in some indicator and they'll say, well, what color does phenolphthalein change to? Because here we're actually getting more basic, phenolphthalein would change to a pink color on this side here. How about at the anode? At the anode side here, your reaction H2SC, we bubble it in as a gas, it solidifies as Se solid. So the mass of the anode also increases. Even though carbon doesn't do anything, it's the location where oxidation occurs. It's where electrons were actually dropped off. The anode, the mass actually increases. And in fact, the acidity is actually going to increase as well, because as a product, we end up generating some H+. The acidity increases, and therefore you can say the pH decreases, right? The farther away from 7 I get, the more acidic it is. Those are some observations I can make at each side. They might ask you questions, can you label the electron flow? Be careful, electrons always flow only in the wire. Electrons never jump into solution, and electrons always flow, in this case here, anode to cathode. So from right to left in this picture. What about the salt bridge? The salt bridge was filled with I think I put in LiNO3, so let me double check that here. Yeah, 1 molar LiNO3. The salt bridge has a compound, Li plus and NO3 minus. What we're going to have in general, cations like lithium plus, and earlier we had even H plus here. It might be tiny enough here. Cations flow towards the platinum half cell, because the platinum half cell is your cathode. Right? Cations go towards cathode. Whereas anions, like NO3 minus, NO3 minus is going to drop off this way. As the electrons end up leaving, the NO3 minus will help counterbalance the charge in this on the right-hand side. So anions flow towards, this time is the carbon half cell, and because anions flow towards the anode. Okay. So what I want to show you here is electrons only flow through the wire, whereas cations and anions, these ones here can flow through solution, and these ones here will, in some sense, complete the circuit for us. Okay. I do want to show you sort of another style of how this question here can be worded. It's a little bit strange. Okay. So this time I'm not going to tell you what the metals or non-metals are this time. So just a new example. Let's take A plus 2, gaining 2 electrons, becoming A. B plus 2, I want to keep on a fair playing field here. C plus 2, giving you 2 electrons, right? So they're not helping out here because they're not actually telling you what the chemicals themselves are. But the question is asking, can you arrange these? Arrange by decreasing strength of oxidizing agent. Or they could have done reducing agent. Okay. They're going to give you one other statement here, just sort of experimentally here. They end up finding A plus 2 reacts with C, but not with B. Okay? So let's see if we can translate this question here first. They want to know decreasing strength. So I want to go from strongest to weakest, from the best to the worst. Okay? They want you to order these for oxidizing agents. What do you know about an oxidizing agent? An oxidizing agent helps something else oxidize. Itself gets reduced. So I could actually translate that, and I can say, can you just order these with the best guy that reduces to the worst guy that reduces? On the table, the guys that reduce, notice that they've already written as a reduction for you. They've written reduction left to right. The best guys that reduce are at the highest part of the table. Now, because they didn't tell you what chemicals they are, I can't just look on the table and see which one's higher. What I need to do is I need to use this experimental finding to sort of order it, which one will be on top, then next, going weaker. here's what you're going to do. You're going to take the statement as is. It tells you A plus 2 does react with C. So we're going to assume one-way arrow. We're going to assume that A plus 2 converts itself to become an A, while C converts itself to become a C plus 2. So that's the first reaction. A plus 2 does not react with B, though. So let's go A plus 2. When I try to react with B, the reaction doesn't go forwards. One way of thinking about that, if it's 0% forwards, it's actually because it's a no reaction. It's 100% against it in becoming A and B plus 2. Let's label who are our oxidizing agents, or who are the chemicals that get reduced. The chemicals that get reduced are A plus 2, B plus 2, and C plus 2. So what you'll notice is a competition is set up. A plus 2 and C plus 2 are both trying to reduce, or both try to gain electrons. A plus 2, B plus 2 are trying to gain electrons. This is in our acid-base chapter when we talk about sort of which side is favored. Well, if I have two guys potentially that can gain electrons here, and you tell me that the reaction actually goes forwards, who's stronger, A plus 2 or C plus 2? Well, in this case here, you should be able to tell me, well, A plus 2 is actually better at gaining electrons. That's why it wins. It knocks the equilibrium over that way. So therefore, from the first statement, we know A plus 2 is actually stronger than C plus 2. Okay. What about the second statement? Between A plus 2 and B plus 2, both of them can reduce, both of them can gain electrons. Who's stronger? Well, since A plus 2 can't actually kick the equilibrium or the reaction to the right, it's actually B plus 2 that actually ends up winning out. The B plus 2 is actually stronger. Okay, and because B plus 2 is stronger, we can then conclude B plus 2 is stronger than A plus 2, which you had already decided is stronger than C plus 2. So in terms of the ordering on this table here, this B equation here should be a little bit higher. It's B plus 2, then A plus 2, then C plus 2. You see, based on the experimental finding here, they can actually, we can actually order them. Okay. Another sample equation that I can do here. Let's say we have A as a metal, right? A plus 2. On the other side here, we have B as a metal. Okay. Remember, our table is always written at 1 molar concentrations. We would have 1 molar A plus 2, 1 molar B plus 2. Okay. Let's say for argument's sake here, based on this, right, if the B were higher, B plus 2 gets to react. So my reaction is B plus 2 gains 2 electrons, becomes B. A is going to become A plus 2 and 2 electrons. Okay. But everything currently is 1 molar solutions. This is going to give me a voltage. What I want to know is what happens for this question. What happens to the voltage? What happens to the voltage if A, we dilute A, and what happens to the voltage if I dilute B? Okay, so it's simple as let's just add water to one side or add water to the other side. Okay, I'm going to put some numbers to this here just for ease here. Let's say this oxidation here, let's say that voltage here is quoted at a voltage of 1.5 volts. Okay, so that half cell, maybe 1.5 volts better than the hydrogen cell. If I add water to the cell, remember at the end of the day, these reactions here are equilibria, right? I've just wrote it as a one-way arrow because I know, yep, this is going to be the oxidation. Upon diluting A, you would have brought the concentration down. As you bring this concentration down, how does the totality shift? Because the equilibrium is going to shift forwards, and going forwards was already a positive voltage, we can say then the equilibrium shifts right, and therefore the E cell increases. We're going to get even higher than 1.50. Okay, let's try the other case here. Let's say the E naught for this one here, let's say it's actually not as positive. Let's say 0.25 volts, okay, for the reduction potential. Okay, let's do part B. If part B I dilute B, I end up pulling down B. Wait a second, B plus 2 needed to gain 2 electrons to actually become B. That's the only way for me to get positive 0.25. If I pull this down, the equilibrium actually shifts to the left. It actually makes it harder. This actually happens as the battery naturally runs. We gradually lose B plus 2 ions. What's going to happen is the equilibrium ends up shifting left, and therefore your voltage or your E cell, your voltage actually decreases. And in fact, what ends up happening here is our batteries, maybe 1.5 volts or whatever, 9 volts, whatever it begins with, we can make this conclusion here. As the chemicals get depleted as they get used up. The overall E cell, the overall voltage from the battery, the E cell actually drops to 0 volts. At 0 volts, we've actually hit a situation where the entire spontaneous equation has now become an equilibrium. Not just equilibrium for each part, but overall it's an equilibrium. At equilibrium, we actually have a dead battery. Okay, that's when you need to just toss it out and then get a new battery. Okay. What I want to introduce to you in this section here is a few sort of side applications. Starting off here, what's a very common battery that we see in everyday life, aside from like AA, AAA sort of batteries? One is inside our car batteries. They sometimes want you to know this equation, so I'm just going to show you what ends up happening in a car battery. In a car battery here, we have one container. We're going to have a lead plate, and we're going to have a lead sulfate plate, PbSO4. We're going to have sulfuric acid as a catalyst inside this container here. I'm going to show you the two reactions that ends up happening. As the battery here is discharging, when you're actually running the car, what's actually happening is the lead and the PbO2, in the presence of H+, it's acidic. We do have HSO4 minus, because as a strong acid it would have broken up to become HSO4 minus. This one here ends up giving you PbSO4, so let's balance that for you here, and 2 water. This is why we call this one here typically a lead acid battery, where the acid is usually sulfuric acid. Okay, so let's see if we can make a prediction. Can you tell me who got oxidized and who got reduced? The best way to do it without having to balance everything, let's assign oxidation numbers for everything. The lead here is starting out elemental. Later on, lead is in the +2 state. If lead goes from 0 to 2, that's a gain of 2. That's lead having increased oxidation number, and increased oxidation number means an oxidation. So lead gets oxidized, lead loses electrons, that's the way its charge goes up, and then it gains PbSO4. PbSO4 is a solid that ends up coating this side here. So PbSO4 is an insoluble precipitate. What about the other one? The PbO2 goes from lead being in the +4 state down also to Pb as a +2. This is sort of like that disproportionation reaction where we had one chemical do both reactions. This time we have two chemicals, but they both become the same PbSO4. This one here is an insoluble precipitate. So going from 4 to 2, we now know this one here was reduced. This one here has gained electrons. This should be PbO2. The PbO2 as a metal plate here ends up also depositing PbSO4. Now, even though in this chapter here we've been learning sort of ideal cases, right, 1 molar solutions and everything, this time here there's a little bit of engineering involved. If we actually now have formed PbSO4, that one there as a solid, being insoluble, it actually coats the electroplate. It actually blocks off the lead from actually encountering more acid particles, more sulfate particles here. In this case here, if the lead and the PbO2 plates here, if they can no longer actually touch the solution, there's no more reaction. So this happens when the battery is dead. What you can do is you can actually recharge this battery. We can use electricity. We'll do this a lot in the next couple lessons here. We're going to use electricity. We're going to force this reaction backwards. We're going to try to erase some of this PbSO4, exposing fresh Pb solution. When I expose fresh Pb solution, now the Pb is in contact with the acid again. Now it can discharge again. And most batteries can, as it discharges here, it's going to gradually build up a deposit of PbSO4. You can then sort of charge and recharge over and over again. Okay, so that's one common battery. If you look in your workbook, you also see how a dry cell works as well. But we'll just leave it with that. Second application here is the whole notion of rusting. Okay, rusting, they can also call this a corrosion. Okay, corrosion is a spontaneous reaction. It just naturally happens. Nobody wants it to happen, but it happens to be a very, very slow reaction. For rusting here, typically we look at a metal. Let's take iron as an example. So iron currently here is in the iron solid form. Turns out for rust to occur, the sort of ingredients that you need for rust here is you need to have water droplets. You need to have a sort of moist environment. You also need to have a really sort of oxygen-rich environment as well. Because what's ending up going to happen is if I take iron, and if this Fe ends up oxidizing, that means losing electrons. If it ends up becoming Fe+2, or maybe another reaction Fe+3, it actually turns out these Fe+2 and Fe+3, in the presence of oxygen and water, it can actually gain electrons. So first was this loss of electrons. I'm not going to balance it for you here. In the presence of an oxygen-rich environment, half O2, and the presence of water, this one here, if it's allowed to reduce, this is going to end up forming hydroxides. We can end up getting compounds where maybe the iron reacts with oxygen itself, end up giving you iron oxides like FeO, like Fe2O3. It can be these irons. Maybe the irons end up reacting with hydroxide. That ends up forming rust products of FeOH2, FeOH3, things like that. And these iron-styled compounds are known as rust. Okay. Other metals will also rust as well in the presence of oxygen and water. Okay. So what we have here is, if we want to prevent rust, we want to keep iron in the reduced state. If iron never becomes Fe+2 or Fe+3, it can never end up later on reacting and end up forming these solid deposits. So what they want to know here is, because rust is always unfavorable, what can I do to actually protect from corrosion or prevent corrosion? So sort of some preventing methods. Okay. So prevention from this corrosion. The one easy way is, well, since an oxidation-reduction reaction needs both halves to occur, if the half that occurs is oxygen and water, if I can separate the oxygen from the iron layer, if I apply a layer of sort of non-polar paint, if I can sort of remove the oxygen and the water from even touching iron, even if iron wants to oxidize, it can't. So this is sort of a physical solution here. We can separate from environment, separate from the surroundings using maybe a non-polar paint layer. Okay. Right. So if I can totally don't let any collisions occur, good energy, good geometry there, then no rust. Good, I've solved it. Okay. This is why people are really concerned. Let's say you get just a small scrape, it just chips the paint. Well, most of the paint is still on there. Why am I so scared of it? The paint was used to actually protect the metal underneath. Even if there's just a small little gash in the paint here, whenever a moist environment, water and oxygen can actually get at it, that can actually start rusting the iron. That's why very quickly we do want to spray it over. We want to make sure to reapply the paint. Even though most of the paint is still there, we want to make sure that there's no gaps in it. What we can do here is we can actually do some other redox procedures in doing this. We can actually apply a voltage. We're going to see this a lot more in upcoming lessons. Apply a voltage to keep iron reduced. Right? Since these ones here are all half cells, right? If I provide enough electrons, any potential iron ions I have so many electrons, the iron gains it. The iron sticks in this iron solid state here. If iron is not allowed to oxidize, again, no rust. Okay. So sometimes we're told ships actually do this. They actually apply a really low current to the outer body of the ship here, and it's actually used to force the iron in this reduced state. The one really cool case here is, if I don't actually just need to apply a voltage, what you can do is you can actually do something called cathodic protection. So let's see if we can take apart that name here. The cathode, right? Cathode is the site of reduction. This time what we want is we want to keep the iron reduced. So let's keep the iron at the cathode. Keep iron reduced, keep iron in the solid form. Okay? And how this is going to happen is, because my table actually lists for me, so it's written as reduction. So we have the Fe equation, Fe plus 2 ends up gaining 2 electrons, becoming Fe. This one here occurs at negative 0.45 volts, right? So Fe plus 2 is trying to gain electrons, is trying to reduce to become Fe. Fe might oxidize with positive 0.45, but there are chemicals that are actually better at oxidizing. They're lower on the table than the iron is. So for example, Fe is starting out there. We can throw in some aluminum. Well, aluminum actually oxidizes better than the iron. We're going to end up getting aluminum ions, Al plus 3 and 3 electrons. Because this one here is lower on the table, this guy gets to oxidize. The iron is out of luck. The iron is stuck in the reduced form. So we're actually sacrificing. Aluminum is known as a sacrificial anode. How this would work out sort of engineering-wise, let's imagine we have a pillar made out of iron. I'm worried about this rusting. Let's put in contact, let's put an aluminum metal plate by it. Between aluminum and iron, aluminum is better at oxidizing. Aluminum ends up becoming Al+3. Sure, you might form rust with the aluminum. Hopefully aluminum is a cheaper metal. The rust will end up forming with the aluminum, and the iron is stuck in the reduced form. The iron is going to be protected from rust. Once the aluminum is totally rusted over, I just remove that, and then I put the iron back on. Okay, maybe a new sample of aluminum. Okay. So these are just some sort of side questions that they can ask you here. This last part here is probably the most important application we're going to do, and this is the application to a redox titration. Okay, so I'm just going to hint at how this titration ends up looking. A lot of it we already know. Titration is a chemical technique. This one here is a technique to find an unknown concentration. By this point here, you've actually learned quite a few titrations. We've done a solubility titration, chloride titration. We've done a lot of acid-base titrations. This time here, the only thing is we're going to deal with an electron transfer as a reaction. At the end of the day, though, it still boils down to a stoichiometry problem. Let me just hint at how this is usually set up. The first main setup is actually using permanganate as an oxidizing agent. So the reaction that I'm going to run involves permanganate, like we did in the warm-up question. The oxidizing agent helps something else get oxidized. Remember, itself gets reduced. Itself reduces. So let me just show you that equation here. This one here is actually fairly high up the table. It's already balanced for you. MnO4 minus and 8H plus and 5 electrons becomes Mn plus 2 and 4 waters. Okay. The nice thing, why did I use this one? First thing, MnO4 here is a strong oxidizing agent. It's going to be able to help something else oxidize. It reduces very well. Okay, so it reacts with many things. The other advantage is MnO4 minus is actually a really deep purple color. It's actually so purple that, let's say I put it in a burette here. It's so purple that you can't actually see the bottom of the meniscus. This meniscus here, strangely enough, it actually forms a meniscus going upwards. So that one we actually read the top of the meniscus. Right? It's so color intense here that we can't actually read the meniscus easy. So this is a deep purple. As the reaction occurs, it ends up converting the MnO4 minus into Mn2 plus. Mn2 plus here is actually colorless. Okay. So, for example, we have a really, really deep purple thing in the burette here. Let's say I was titrating against an iron solution. And the iron solution here is much simpler. Let's just go iron plus 2. In becoming an iron plus 3, it has lost an electron. Okay. First thing we need is we need a balanced equation. So we have our half equations. I would need to scale this equation up by 5 to make sure that all the electrons are accounted for. My whole equation ends up being permanganate NaH plus with 5 irons. I just chose something random in oxidizing. Becomes 5 iron plus 3, and we have our Mn2 plus, and we also have water. Because the equations on the table were already balanced, this balanced equation here should now be balanced. And what we're actually doing is we're dropping this really intense purple permanganate solution. Usually they call it potassium permanganate. It's just a soluble salt that tells you about permanganate. And what I'm doing is I'm dropping it up slow enough that I'm using it to actually count how many iron plus 2s are in solution. So let's see how this would happen. As I drop in a drop of purple, if this MnO4 minus still senses iron 2 plus, it's going to convert from the purple form to the colorless form. So you drop in a purple solution, it kills iron, it stays colorless. You drop in another drop of permanganate here, as long as it finds iron, it's going to convert over, it's going to become manganese. That's the equivalence point. That's when all the iron has been used up. What I want to do now is I want to drop in that very last drop of permanganate. Now the permanganate doesn't find any more iron 2 plus. I've already hit the equivalence point. Because it can't find any iron anymore to oxidize, the permanganate will stick around. We know this reaction is done when the color stays purple. So this is kind of nice here. Not only is it a very strong chemical, it oxidizes many things. It also is self-indicating. I don't need to throw in another indicator to change color. When this one here starts appearing purple, that's because the manganate ion actually couldn't find any more iron to oxidize. With that in mind, at the end of the day, it just becomes a stoichiometry problem. So let me just hint at it. Let's say we do this. I need 17.52 milliliters of 0.1000 molar. I might even say KMnO4. Well, KMnO4 is an alkali salt. It 1-to-1 ratios and gives me how much manganese ion there is. Okay, we definitely need to have acidic conditions. So usually we throw in an excess of maybe HCl. I don't really care how much there is. I just need to make sure there's H+, so that if there's iron, this permanganate ion can actually react. And let's say my initial volume of my iron, it actually started off as 25 milliliters. This looks completely new, but it boils down to a stoichiometry problem. You take the chemical that you know more. Let's find moles. Why do I need moles? From the balance equation, sure, it's a redox equation now. But the balance equation still says a 1-to-5 ratio. I can do times 5 pretty easily. And then I can utilize this last number here with the 25 mils and end up calculating the concentration for iron. Okay, so let me just do that for you here. What is the concentration for iron solution in this redox titration? Let's convert the 17.52 into liters, 0.01752 liters. This one here, they said KMnO4, but that's 1-to-1 ratio with the permanganate. The concentration was 0.1 molar, 0.100 moles per liter. Here's the mole ratio. Here's the part that we needed to know. Oh, it's a redox titration. Well, it's the 1-to-5 ratio that we care about. We have 5 Fe plus 2. That now gives you moles of Fe plus 2. So let me write that down here. And then lastly, we're going to divide it by the starting volume. I would have totally screwed up the volume here. It would be totally diluted here. Sort of unfortunate because I'm dropping it from the burette. But all the iron that I count was initially just in 25. So I'm just going to divide it by 0.0025, 25 milliliters in liters. Okay. So 0.01752 times 0.1 times 5 divided by 0.025. Even though it's a redox titration, it boils down to a stoichiometry problem. That is my unknown concentration of Fe plus 2. Okay. Now that's great. That works for things that get oxidized. What about things that I want to actually reduce? Okay. This one here is a little bit more complicated. I'm just going to walk you through what happens. What we're going to use is we're actually use iodide very commonly as a reducing agent. Okay. Again, translate that for yourself. A reducing agent helps something else reduce. Itself gets oxidized. Okay. Not the definition, but that's going to help you find it here. The reason why this one here is a little bit more complicated is because this one actually takes place in 2 steps. The first step involves taking any iodides that you have and converting the iodide to become iodine, I2. That one there is an oxidation, right? We had expected the I- oxidizes. Strangely enough, as a second step, we're going to seemingly undo this. We're going to take the iodine and we're going to let it gain the 2 electrons and actually let it go back to 2I-. Well, what was the point in that? Why convert to iodine and then convert back to iodide? It turns out for the second reaction, what we're going to do is we're going to count it more closely. We're going to perform the second reaction with thiosulfate. We're going to actually have 2S2O3 minus 2. This is actually the thing that's going to oxidize S4O6 minus 2 and 2 electrons. And essentially what happens here is I'm going to use the second titration. The S2O3 is going to help count the I2 for me. The I2 would have come from I-, and that's actually going to help me do my titration. Okay, so let me just draw a picture of how this works. And your textbook has some examples of this here. Let's start off with a bleach solution. A bleach solution, the active ingredient is this OCl-. What we're going to do first is I'm going to toss in an excess of Ki. Oh, where'd the potassium come from? Again, I'm never going to have a bottle of just pure iodide. That would be unstable as like an I- ion. Ki ends up breaking up to become K plus and I-. And in this question here, I don't know the molarity of the OCl-. Okay, so what I do is I toss in a ton of I-. What I want to do is make sure that the OCl- reacts with the I-, converts all the I- into I2. All right, let me show you that step 1. So for this reaction, step 1, OCl- reacts with the I minus. This one here does have to be acidic. So let me actually balance this for you. 2I minus and 2H plus. This one here converts it over. We get Cl minus, we get water, and we end up getting I2. Okay. Now, remember I was saying it was an unknown amount of OCl minus. I don't actually know the concentration. What if I toss in too much I minus? Turns out no problem. I toss in all the I minus. As long as there's OCl minus and there's I minus around, it's going to have converted a bunch of my I minus. It's going to have converted the I minus into the I2 form. I'm not doing the counting really closely there. In fact, at this point here, I might have a ton of I minus. I might even have extra I minus around. No problem. Because in step 2, that's when I'm going to perform my titration. That's when I'm going to be a little bit more careful. Step 2 is the thiosulfate titration. I'm going to take the I2. I'm going to count how much I2 I have using this 2S2O3, using this thiosulfate. This is going to seemingly be crazy, right? Why am I converting it back to iodide? I'm going to take any iodine that I formed in the first step, and I'm going to force it back into the iodide. But I'm going to do a really good count of that. So what happens here is, let me just make up some numbers. Let's say for my second titration, let's say it takes 12.34 milliliters of 0.500 molar S2O3 minus 2. That's how much I add. That's what I do with my bread and all that. I use this to count moles of I2. Well, why did I have I2 to begin with? Well, I2 actually was a product from my first equation. Whatever moles that I get for I2 is actually in a mole ratio with OCl minus, and therefore we can actually calculate the unknown concentration OCl minus. Again, I'm just going to hint at how you do this. Your workbook will have more practice here. Let's figure out here what's the unknown concentration OCl minus. I haven't really given you a lot of information. Let's start off with where we know the most. So thiosulfate. From the burette, you need 12.34 milliliters on average, 0.021234 liters. This one here is thiosulfate, S2O3. Take the concentration, 0.5000 moles for a given liter. I'm going to then use the mole ratio. For every 2 moles of S2O3 minus 2, that's a 2-to-1 ratio with iodine, because the S2O3 actually reacts just with the I2 complex. And the I2, well, how come I had I2 to begin with? It was all I minus. The I2 is in a 1-to-1 ratio with OCl minus. I can end up going, for every 1 mole of I2, there's also 1 mole of OCl minus. If I knew the initial concentration of OCl minus, I can just divide it like we just did earlier. Okay? So even though it's 2 steps, we're a little bit more careful in step number 2. It seemingly sort of reverts back to what we did before, but just everything is in mole ratios. I do both mole ratios, the mole ratio for step 2 and the mole ratio for step 1. One last little note here. In order for us to figure out how much iodide there is, or even iodine, usually we throw in a little bit of starch as an indicator. Turns out when starch is in the presence of I2, this one here actually turns to a deep blue solution. The iodine itself is already a little bit purplish here. There already would be a little bit of maybe even a brownish undertone as well. But by throwing starch in, it's going to be deep blue. You're going to keep tossing in the thiosulfate until the blue color is gone. When the blue color is gone, I know that's when to stop, and that's when to take the volume reading. Okay, I'm going to practice one of these questions with you probably more so tomorrow, but that's just another application for these electrochemical cells. Okay, let me know if you have any problems. Thanks, guys.